To this point, we have talked about accelerations, and then pursuant to accelerations, we've talked about displacements and velocities, and lots of different ideas that describe the motion of objects. What we haven't talked about, strangely, it seems kind of backwards, but here we are. What we haven't talked about is the reason that an object is going to accelerate in the first place. So now we need to back up a step. We've talked about accelerations in kinematics, but those are not fundamental principles. The fundamental principle that we haven't dealt with yet is the idea of a force. We all have a working knowledge of what a force is, and in some ways the working knowledge that we have, I think, is maybe the best we can do. So let's talk about the definition of a force. And the definition I'm going to give you is not mathematical, it's intuitive, and that's, I think, the best we can do. And that's not to say there might be something better. I think this is the best way to approach it. A force, you can think of it as an influence on an object that has the potential to accelerate that object. In other words, it has the potential to change what that object is doing. A good example, right? Let me just let my pen lie there. If I want to change what the pen is doing, right now the pen is not doing much of anything, it's just lying. If I want to change what it's doing, I've got to exert an influence on it, right? I can flick it around, I can make it spin, I can move it in a straight line, I can make it roll. But the point is, I have to exert some sort of influence on this pen to make it change what it's doing. That influence that I exert, we call a force. And you can see from this, at least one type of force is going to involve me actually coming in and touching the thing, right? That leads to discussion of the two different categories of forces that we can have. The first we'll talk about are contact forces. These are forces that, just like their name suggests, two objects have to be in contact with each other for this force to be exerted. For instance, object 1 is this pen, object 2 is my finger. As long as they're not in contact, I can't make the pen move, right? I'm not a Jedi. I can't use the force, right? That's one thing Lucas got right about the science. I can't exert a force on this thing without touching it. In other words, I have to make contact. So if I make contact with it, I can then exert a force on it and make it change what it's doing. Those are contact forces. The thing that I was doing I was touching it, we usually call that an applied force. That is something, be it a finger or be it a rope or a rod or something, is going to come in and touch another object, and there will be a force applied from that. There are other kinds of contact forces that we know of, probably know of instinctively. Friction's a big one. We're definitely going to do a lot of work with the friction force and what that looks like. But we have a good idea what friction is, right? We all do this in the winter to warm our hands up. We probably know that our brake pads on our cars push something against our brake discs that causes friction and slows them down. So friction force is a good one to think about. We find forces in ropes or strings, and we normally call those tension forces. Again, we're going to do a lot more with those. I'm just giving you some examples of some things you might know. Tension forces, but how does a rope exert a force on something? Well, it has to be tied to it, right? It has to touch it. That's a contact force. And there are other ones, of course, which we can talk about as we get to them. But that's our first category of forces, which are contact forces. So category 1. Category 2, and there are only 2 categories, well, that would be non-contact forces. These are forces that don't have to touch things to exert forces on them. The main one, really the only one we see in this course, is the force of gravity. If you go on to physics 2, you will see the electric force and the magnetic force, which are examples of non-contact forces. Gravity is the one we deal with here. Gravity doesn't have to touch you to exert a force on you. For instance, right now, gravity is exerting a force on me. Where does gravity come from? We're going to learn later, if you don't already know, that it comes from the earth. I'm not touching the earth right now. I'm touching a chair, I'm touching the floor, but I'm on the second story in my office. I'm not touching the earth, but the earth doesn't have to touch me to exert a force on me, right? We mentioned electricity and magnetism. Most of us have had this experience with two magnets where I'm trying to push them together, right? But I feel a resistive force, or if I flip one over, I feel a force pulling them together. I don't have to touch them to feel this resistive force. If you've done this, you know what this feels like. If you haven't, go find some magnets and do it. It's kind of cool. But there is definitely an influence on these guys that is not coming from a contact. So that's a non-contact force. Gravity is going to be the one we deal with most of all in this course. Actually, only in this course. Lots of contact forces, only one non-contact force. All right, what else can we say about forces? Well, crucially to how we proceed, forces are vectors. They have a magnitude, right? I can exert a strong force on something or a weak force on something, and they have a direction. Clearly they have a direction. Let's go back to me pushing this pen around, right? If I exert the force on the pen, the force I'm exerting is that way along my finger. And you can see that that's actually how the pen ends up moving. That might not always be the case. There are some forces that act at strange angles. But the point is, the force has a direction associated with it. It's got a magnitude and a direction, which makes the force a vector. The units of forces, or the units of force, I should say, are newtons, after Isaac Newton, who is responsible for much of the language we use when we talk about force, and most of the mathematics we use when we talk about forces, or at least he's responsible for the calculus. There's some debate about that, but probably was Newton. We're going to see a little bit later what is inside of a newton. Usually when you see a unit that's named after somebody, what we've done is we've taken a bunch of fundamental units that we were tired of writing down 37 times and buried them inside somebody's name. The same thing happens with a newton. We're going to wait till we talk about Newton's second law of motion in a few videos to talk about what's inside a newton. But the units are newtons, they're vectors, and they have units of newtons. One of the ways, and let me say, because they're vectors, we're going to do all the decomposition that we've been doing with kinematics. If I can decompose an acceleration and a velocity and a displacement into x and y components, I can absolutely decompose a force, and I do it the same way. So nothing new there. They're vectors. All right. One of the things I'm going to need to do if I'm analyzing the motion of an object is I need to come up with a way to figure out what all forces are acting on that object. After I do that, I'm going to need to draw some sort of picture to give me the information that I've figured out. So here's the first way to do it. When I'm counting the forces, in other words, I'm trying to determine what forces are acting on any object. I've got a 2-finger rule, right? 1, 2. This is not original to me. My engineering dynamics teacher in undergrad drilled this into my brain, and I've always thought it was good. But I'm going to count up 2 fingers. First finger, gravity. Most of the systems we deal with happen at or near the surface of the earth. Gravity is always going to be with us. Gravity can always be with us even if we're off of the earth. But on the earth, we have a really, really important expression of gravity, which we'll get to later. But gravity is always with us. So that's my first finger. If I'm counting up forces on an object, I've got gravity. My second finger, whatever's touching it. Right? Gravity, whatever's touching it. Now, that second finger might be 8 different things. But notice that this matches up pretty well with our categories of forces, right? Contact forces, that's whatever's touching it. And then gravity, that's gravity. I know that's a surprise. But if I can just count up whatever's touching it, and the assumption then is if something is touching it, there is a force exerted from that contact. All right. So once I do this, once I have determined what all the forces are acting on an object, I can summarize that information graphically with what's called a free body diagram. Free body diagrams are very, very special drawings. And only certain things should appear on free body diagrams. I'll tell you what they are. Only include forces and angles. That's it. We don't include anything else. And on the forces, if I'm looking at a free body diagram of an object, these forces are only the forces acting on the object. That's important because very often I have an object and forces are acting on the object, but that object is also exerting forces on other things. The only forces that I include are the ones acting on the object. I don't care what that object is doing to other things. If I need to draw a free body diagram of the other things, they might include that force. But of an object, I only draw the forces that are touching it. Let me give you an example. Someone is standing on the ground. Okay, fair enough. This is not a free body diagram. This is just a picture of a person. What I want to do is determine the free body diagram of this person. In order to do that, I've got to figure out what forces are acting on this person. In order to do that, I go to my 2-finger rule. My first finger is gravity. So I need a way to illustrate gravity acting on this person. To draw a free body diagram, I'm not going to draw a person. I'm going to represent that person as a dot. Now, that person, because this is a physical universe, has some sort of mass. And it is appropriate at this point, because mass is going to play a central role in what we do with forces, to just label this as some mass. I don't label it as a person. I label it as some mass, because that's what about this person I'm going to worry about if I'm dealing with forces. Okay, so I label this as a mass. If there's more than one of them, I'll label M1, M2, so on and so forth. I just have one person, gets represented as a dot, mass. All right, 2-finger rule. First finger is gravity. How do I represent gravity here? I hope we know that gravity acts downwards. So what I'm going to do is I'm going to draw an arrow down, and that will represent gravity. And for now, I'm going to call this F sub capital G for the force of gravity. This is not a 6, as my 8-year-old likes to tell me my G's look like 6s. I realize that it's a capital G. Force of gravity. Later, we're going to learn how to represent this another way, but force of gravity works okay for now. All right, that's the first finger, gravity. Now, whatever's touching it, well, what is touching this person? Well, most of you would say, well, the air is touching him, and that's true. We're going to ignore air resistance for the bulk of this course, and so even if we don't, he's not moving, right? He's just standing there. So air resistance, I don't think is going to come into it. But he is touching the ground or the floor or whatever. So there's going to be a force exerted on this person from the floor or the ground or whatever he is standing on. How do I represent that? Well, for reasons that I'll tell you about in just a second, I'm going to draw an arrow upwards. And I'm going to call this the force of support. Why do I call it that? Because he's standing on the ground and the ground is supporting him, right? If the ground wasn't there, he'd fall. Fair enough. This is the force of support. Now, if you've had physics before, you're probably kind of screaming inside, oh, normal force. What's the normal force? So normal is a word we need to talk about. So let's do that now, and then we're going to come back here. So let me take a little aside. We're going to encounter lots of forces that people are going to want to call normal forces, and that's okay as long as we know what that means. Chances are, many of you don't. Normal, not in the sense of ordinary, but the mathematical normal. Normal is a mathematical word which just means perpendicular. You can also use the word orthogonal, which is my personal favorite. And usually these two are interchangeable. Orthogonal is a little bit more rigorously defined than perpendicular. But it's okay. In this class, we can go either way with that. So all three of these words mean the same thing. Normal force, or normal means perpendicular, means orthogonal. And we know what perpendicular means, something like that, right? So what are we saying when we're talking about a normal force? As it turns out, if we're talking about contact forces with surfaces, we got to be careful because I'm not talking about contact forces with ropes or things like that. Contact forces with surfaces are often, and I'm going to have to be really careful here because we're going to see later friction is a contact force with a surface, and friction doesn't fit into this, but I'll just say this and we'll deal with the exceptions when they come up. Contact forces with surfaces, I'm not even going to write often. Contact forces with surfaces are perpendicularly directed. Perpendicular to the surface, You could say normally directed. You could say orthogonally directed. And I'm going to just put in parentheses here, not friction. Because friction is a contact force that involves a surface. It's not exactly what we're talking about here. So just to cover my own posterior, we'll say not friction. But for contact forces like what we saw in here, they're going to be directed perpendicularly or normal to a surface, which means if you have someone standing on a hill, right, the force of support from the hill on this person is actually directed like this, perpendicular to the surface. Over here, we don't have a hill. We just have the man standing by himself. Sorry. Sharpies bleed. Save my desktop. Put another piece of paper under it. So I have this support force that is perpendicularly directed or normally directed. Because of that, many of you have been taught to call this a normal force, and that is okay as long as you understand what that means. I find lots of normal forces on free body diagrams that shouldn't be there. There's not some great cosmic normal that just passes out forces as you need them. A normal force is just talking about the orientation of that force. You got to know where it comes from. In this case, it's the force of support from the floor. So do I care if you write normal force on your free body diagrams? No, I don't. As long as you understand that normal is not a source of the force, it is a description of the force. You've got to keep in your mind at least the source of this force, which in this case is the floor or the ground. So this, and I think that's all that's touching him there, right? We've got gravity and we've got whatever's touching him, and I think that works here. So this is the free body diagram of this particular person standing on the ground. Okay. All right, we're gonna stop it here and do another video on another free body diagram to see some more forces in action, but we'll cut this one off here.